Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 34th lecture of the course Discrete-time Markov chains and Poisson processes. So, today is going to be the last lecture of this course and we will end with another concept which is of compound Poisson processes. So, let us see what it is. So, a stochastic process xt is said to be a compound Poisson process if it can be represented as this kind of a random sum. So, what is xt? Xt is I running from 1 to nt, summation I running from 1 to nt of yi, where what is nt? Nt is a Poisson process with some rate and yi's are iid random variables with some distribution which is also independent of nt. So, xt is this kind of a random sum where this upper limit of summation nt is a Poisson process with some rate lambda and these summands are iid random variables, but also important thing is these yi's are also independent of nt. Fine. So, if xt can be written in this way, then we say that the process or the stochastic process xt is a compound Poisson process. Fine. Now, remark, so if nt is Poisson with rate lambda, so here if nt is Poisson with rate lambda, then this expectation of xt where xt is of this form, or in other words xt is a compound Poisson process, is given by lambda t times expectation of y1 and variance of xt is given by lambda t times expectation of y1 square. Fine. So, here we will not prove these formulas, but I strongly encourage you to try proving these two formulas, formula of expectation of xt and variance of xt by conditioning on nt. Fine. So, again I strongly encourage you to do that exercise of finding the expectation of xt and variance of xt if xt is of this form where nt is a Poisson process, yi's are iid random variables. Again we are assuming here that yi's have mean and variance, then only we can talk about mean and variance of xt. So, we are assuming that yi's have mean and variance, or the first, and I should rather say yi's have first and second moments. So, we are assuming this, then only these formulas are valid, that expectation of xt is lambda t, which is basically expectation of nt times expectation of y1, and variance of xt is again lambda t, which is expectation, or you can think of it as variance of nt because nt is a Poisson, nt is Poisson lambda t. So, its mean and variance is same, it is lambda t, but one thing you should be careful about. So, here it is not variance of y1 square, variance of y1, but rather the second moment of y1 square. So, one thing why I am just y1, remember these are all iid. So, expectation of yi is same as y1 is same as expectation of yi for all I, and similarly this is equal to expectation of yi square for all I. So, since this is IID, so this is just stated in terms of y1. So, expectation of xt is lambda times expectation lambda t times expectation of y1, and variance of xt is lambda t times expectation of y1 square. So, you should be careful here, it is not variance of y1 square, but variance of y1, but expectation of y1 square, the second moment of y1. Fine. So, again I will not work out this. So, I have just given it as a formula, I will not prove these two formulas, that namely how do we get expectation of xt as lambda t times expectation of y1 and variance of xt as lambda t times expectation of y1 square, but I strongly encourage you all to try and prove these two formulas by conditioning this, like the standard conditioning argument, but here conditioning on nt. Fine. So, you will see that is where you will use all those facts that nt is independent of yi and so on, but I am not going to do all those things in this course, but I strongly encourage you to do those two exercises. Fine. Okay. But you should keep in mind these two formulas, the expectation and variance of a compound Poisson process if nt is Poisson with rate lambda. Now, so we have defined this new class of stochastic processes, namely compound Poisson process. Now, where does such processes arise? So, let us see a couple of examples. So, suppose that buses arrive at a sporting event in accordance with a Poisson process, and suppose that the number of fans in each bus are independent and identically distributed. Then if I call then xt is a compound Poisson process where xt denotes the number of fans who have arrived by time t. So, buses are arriving. So, you have a sporting event, say some sporting venue, say some stadium where some match is going to happen. Say buses are arriving according to a Poisson process with some rate lambda, say some rate, and further the number of people that each bus brings, that is IID, with some distribution. Then if you are counting the number of fans who have arrived at the stadium up to time t and call it xt, then that will be a Poisson, that will be a compound Poisson process. Why? Because you can write it in this form, that xt. So, what will be the total number of people who have arrived up to time t, or total number of fans who has arrived up to time t? It should be just I running from 1 to nt, fine, or not 1, but 1 only. So, yeah, that is how we wrote it. So, I running from 1 to nt yi, fine, and so we will basically follow the convention. So, if nt is 0, then this sum is 0. So, here you can say, so nt can actually be equal to 0. In that case, what is this sum? So, if nt is equal to 0, then xt is equal to, or this sum we will say that this is sum is equal to 0. That convention we are following, fine. So, in that case, so if yi is the number of fans who come in the ith bus, then up to time t there will be nt arrivals of bus. So, the total number of fans who will arrive up to time t will be given by this formula. So, you see again compound Poisson process arrives very naturally. Another example, suppose customers leave a supermarket in accordance with a Poisson process. If yi, the amount spent by the ith customer for I equal to 1, 2 and so on are IID, then xt is a compound Poisson process where xt denotes the amount of money spent by the customers, again not who arrived, who left up to time t, fine. So, or basically let me keep it as arrived only, and this one let me say that customers arrive, fine, again it does not matter. So, suppose customers arrive at a supermarket in accordance with a Poisson process, if yi is the amount spent by the ith customer for I equal to 1, 2 and so on, and suppose if that amount is iid, then if you denote by xt the amount of money spent by the customers who spend up to time who arrived up to time t, then again xt will be compound Poisson because it will have this kind of a expression, right, because here now yi is the amount spent by the ith customer, nt is the total number of customers who arrived up to time t. So, the amount spent by the customers who arrived up to time t is given by this. So, again you see this is a very real life situation, the amount spent by customers in a supermarket. So, again that can be modeled by a compound Poisson process provided like the arrival process is Poisson and the amount spent is iid. Fine. So, again all these assumptions are needed, only then you can say that it is a compound Poisson process, but you can see like again you can use compound Poisson processes to model very real life scenarios. Fine. So, compound Poisson processes are not like just we have not defined such a process just like that, but those are important processes in the sense it can be used to model many real life scenarios. Fine. So, we will end with one example or one problem on compound Poisson process. Suppose that families migrate into a territory according to a Poisson process with rate lambda equal to 2 per week. Fine. Now, if the number of people in each family is independent and takes the values 1, 2, 3, 4 with these probabilities, then what is the expected value and variance of the number of individuals migrating into the territory during a fixed 5-week period. So, again here the unit is per week. So, per week, so the families migrate into a territory according to a Poisson process with rate 2 per week. Fine. Now, each family that migrates will have 1, 2, 3 or 4 members with certain probabilities. Now, you are asked the mean and variance of the number of individuals who migrate into the territory in a given period of 5 weeks. Fine. Okay. Now, let us see how can we solve this using compound Poisson processes. Now, let NT denotes the number of families who migrate into the territory up to time t. So, okay, before starting also remember, so here if the number of people in each family is independent, and again this number is also independent of the arrival process. So, a family independent of everything else will have 1, 2 or 3 or 4 members with probabilities 1 by 6, 1 by 3, 1 by 3 and 1 by 6 respectively. Fine. And you are asked what is the mean and variance of the number of individuals who migrate into the territory in a given period of 5 weeks. Fine. So, let NT denote the number of families who migrate into the territory up to time t. Fine. Then N dot is a Poisson process with rate 2 per week, that is because you were told that families migrate into a territory according to a Poisson process with rate lambda equal to 2 per week. Let yi denote the size of the ith family that arrived into the territory. Fine. Then, then you are given that these yi's are iid and takes values 1, 2, 3 and 4 with certain probabilities, and it is also independent of the arrival process. Then total number of individuals migrated into the territory during a fixed 5 weeks period is, if you have to write it, then it is x equal to I running from, again not 0, it should be I running from 1, I running from 1 to n5 yi, right, because n5 will be the total number of families who will migrate in a given period of 5 weeks, and yi is the size of the ith family. So, this will be the total number of individuals who migrate into the territory during a fixed period of 5 weeks. So, now you have to find expectation and variance now you already know how to find expectation and variance of compound Poisson processes. So, expectation of xt is lambda t times expectation of y1 and variance of yt is lambda t times expectation of y1 square. So, here t is equal to 5 because the rate of arrival is 2 per week and you are asked for a 5-week period. So, here t equal to 10, t equal to 5. So, expectation of x is lambda times t. So, lambda is equal to 2, t is 5 and now you have to find expectation of y1. So, it takes value 1 with this probability. So, it is 1 times 1 over 6, it is 2 with probability 1 by 3. So, you get 2 by 3, 3 with probability 1 by 3. So, you get 3 by 3 and 4 with probability 1 by 6. So, you get 4 by 6. Now, if you do this calculation, you will end up with 25, right. And now, for variance, what is the formula of variance? That is lambda t times expectation of y1 square. Fine. Now, again lambda is 2, t is 5. Now, you have to find expectation of y1 square. So, it is 1 square times 1 by 6. So, this is this 2 square times 1 by 3. So, you get 4 by 3, 3 square times 1 by 3. So, you get 9 by 3 and 4 square times 1 by 6. So, you get 1 over 6 plus 4 over 3 plus 9 over 3 plus 16 over 6. So, that is just expectation of y1 square, where y1 or yi denote the size of the ith family, and if you do the calculation you get this answer. Fine. So, again you see the main thing is we just wrote down the required thing as a compound Poisson process and then just we used the formula for mean and variance of compound Poisson process. Fine. Okay. So, that ends the course. So, just a very brief recap of what we have done in this course. So, we started with some preliminaries and then we studied discrete time Markov chains in detail. So, we started with the definition, then the first important theorem was that the evolution of a Markov chain is completely specified by the initial distribution and the transition probability matrix. Then we saw this n-step transition probability matrix and so on. Then we talked about this classification of states, recurrence, transience. Then we further subdivided recurrence into null recurrence and positive recurrence. Then we looked at stationary distributions or invariant distributions, when it exists or about its uniqueness, existence. We analyzed all those things for finite state irreducible Markov chains, for finite state Markov chains, infinite state Markov chains, irreducible, non-irreducible. So, we made a detailed study of existence and uniqueness of stationary distributions, and then finally we looked at some limiting theorems. So, that was discrete time Markov chains. Then we learned about various properties of exponential distributions. So, all those properties are of independent interest, but in the context of this course those were kind of prerequisite for studying Poisson processes. And then after doing all those prerequisites, we started with Poisson processes. We saw many properties of Poisson processes, like it has stationary independent increments, the number of arrivals on a given time interval of length t is Poisson with parameter lambda t if it is a Poisson process with rate lambda. Then we saw this Poisson thinning, which basically says if you split a Poisson process, then the splitted processes are again Poisson processes with appropriate rates and they are independent of one another. We also saw a kind of converse to this, that if you have two independent Poisson processes and you merge them, then that is again a Poisson process. And then we saw about this conditional. So, before that we also saw that what are the inter-arrival times of a Poisson process. So, that turned out to be exponential distributions, and that is basically the connection between Poisson process and exponential distributions. And then using that we also got that the nth arrival time has gamma distribution. Fine. So, all these things we saw. Then we saw this Poisson thinning, superposition of two independent Poisson processes. Then we saw this conditional arrival times, so that if you are given that up to a time of t there has been n arrivals, then what is the conditional distribution of these n arrivals or this n occurrence of these n events. So we saw that basically has the same distribution as the order statistic corresponding to n IID uniform 0t random variables. And then finally we ended today's class with this concept of compound Poisson processes, which again we saw is helpful in modeling many real life scenarios, and then we ended with a simple problem using the concept of compound Poisson processes. So during the course we have solved plenty of problems so that the concepts gets clearer, and also in mathematics solving problems is very, very useful. Unless you solve many problems, you will not be able to grasp the concepts properly. So that's why we gave special emphasis on solving problems. During the course we have solved many problems. So that's all. So hopefully the course was enjoyable, and hopefully this will be useful to you in future. So with that, let me stop. Thank you all for attending the course. Thank you again. That's all.